So this is section 3.4, and it's titled Exponential and Logarithmic Equations. We're going to learn a little bit about it by looking at our textbook, and we're going to do some examples together. So do me a favor and write down this as your title for today in your notes, and you guys are going to take notes on this video. So every once in a while, I will ask you to pause the video so that you guys can write down something important from the textbook, and then we'll do our examples together in real time. So let's get started. Go ahead and write down everything that you see in this blue box. Whenever I put up a blue box like this or something from the textbook, it's going to be your notes, and then we'll do an example that follows shortly after that. So go ahead and pause the video and write down everything in this blue box, and when you're ready to move on, you guys can unpause the video. So example 1a, we are looking at solving exponential equations, and from what was written in that blue box up above, it says that we have 3 steps. Number 1, rewrite the equation in the form b to the power of m equals b to the power of n. So I see 2 to the power of 3x minus 8, and I need to rewrite this as 2 to some power. So my first step is to rewrite it with that new base. So 3x minus 8 equals 2 to the power of 4. So now that we have the same base, we can move on to step 2. Step 2 says set the exponents equal to each other. Set m equal to n. So because my bases are the same, then I can say that the exponents are also equal to each other. So we'll kind of cut out the middleman, cut out those bases, and we'll say that 3x minus 8 is equal to 4. And then step 4 says to solve for the variable. So we'll solve for x by adding 8 to both sides and then dividing by 3. So 3x equals 12, therefore x equals 4. And then we can substitute that value back into the original equation to make sure that that actually proves to be a true statement. So if I take 4 and plug it back in here, I get 3 times 4 is 12, 12 minus 8 is 4, and 2 to the power of 4 is 16. So that's correct. Example B says 27 to the power of x plus 3 equals 9 to the power of x minus 1. So in order to continue on this side of it, we need a base that's the same. So I don't know any power of 27, I don't know any power of 9 that makes 27, but I do know something that multiplies into both of these. So I think 3 multiplies into both of these. So I can rewrite this as 3 to the power of 3, and I know that I still have that exponent of x plus 3 up there. So 3 cubed is how I got 27, and then that x plus 3 just stays up in the exponent. And I can rewrite 9 as 3 to the power of 2, and that exponent again just stays up there. So 3 squared is 9, and that x minus 1 stays up in the exponent. So if the bases are the same, then the exponents are the same. So 3 times x plus 3 equals 2 times x minus 1. If I solve this, I get 3x plus 9 equals 2x minus 2. And if I bring everything to one side, I get x equals negative 11. And I want to check to make sure that's true. So if I plug in negative 11 here, I get negative 11 plus 3 is negative 8. And then 9 to the power of negative 11 minus 1 would be 9 to the power of negative 12. And each of those would simplify to 3 to the power of negative 24. So this is the correct answer for part A and for part B. So this is how you would solve an exponential equation. Here's another blue box from your notes, so do me a favor and pause the video and write that down as well. It says, using natural logarithms to solve exponential equations, isolate the exponential expression, take the natural logarithm of both sides of the equation, simplify one using one of the properties, and then solve for the variable. Make sure to have that in your notes. Here's example number 2. So in this case, we're solving another exponential equation. And you might look at this and think, hey, that looks a lot like the previous ones that we just did. However, I cannot think of any power of 4 that makes 15 or any other power that goes into 4 and 15. So the only thing that would multiply to make 4 would be 2, but 2 doesn't go into 15. So that means we cannot use the previous method to solve this one. Instead, we have to use the example of taking natural logarithms of both sides. So in order to do that, we can literally write the natural log in front of both sides like this. So we have ln of 4 to the power of x equals ln of 15. Alright, and then we can use some of our properties of logarithms that we know about. So essentially my end game, we'll go through the steps. Step 1 is to isolate the exponential expression. So that was already isolated by having 4x by itself. Step 2 is to take the natural logarithm of both sides. We just did that right here. Step 3 is to use one of the properties, so either the power property or simplifying logarithms if it was log base e. So the power property says we can take this x and move it down front. So I can rewrite this as x times ln of 4 equals ln of 15. And then last but not least, we can solve for the variable. So if I want to get x by itself, I can divide by ln of 4 on both sides, divide by ln of 4, and I'm left with x equals ln of 15 divided by ln of 4. Now if you had a calculator, you could actually evaluate what that was by plugging it into a calculator, but for right now, I want you to leave your answer in its fullest, or in its exact form, I should say, so you can leave it like this. If you did put it into a calculator, you would get approximately 1.95. So ln of 15 divided by ln of 4 is approximately equal to that. But again, I care about more of the exact answer. And just as a side note, maybe we'll write ourselves a little note over here. You can use any logarithm that you want. You can use any logarithm. But the most often one or the most common one we use, I should say, is the natural log. So ln is the most common. So you could have used log base 10, you could have used log base 4. You would have noticed that if you had done log base 4, you would have log base 4 of 15 over 1. And anytime you use a different logarithm, it's equivalent to this. The only difference is that you would have to use the change of base formula to show that they are equivalent. But any logarithm will work. So log base e works, log base 10, log base 4, whatever you want, but ln is the most common one that we choose. Alright, so let's look at another example using these same properties. Again, let's go back to the notes we wrote down earlier. Step 1 says to isolate the exponential expression. So in order to do that, I have to get rid of this negative 3. And I have to get rid of this 40. I want e to the power by itself. So let's add 3 first. So we get 40 e to the power of 0.6x equals 240. And then we can divide by 40 on both sides. So we get e to the power of 0.6x equals 6. And again, the point of doing that is that I want to isolate the exponential expression. And now I can move on to step 2, which says that we need to take the natural logarithm of both sides. So if I can just rewrite it on the same step, I can take the natural log of both sides. And look here, I have the natural log of e. So log base e of e, remember, this is not correct mathematically, but we can think of those like they cancel. So log base e of e cancels, and I'm left with 0.6x equals the natural log of 6. And then last but not least, my directions say to isolate the variable. So I'm going to divide by 0.6 on both sides, divide by 0.6. Therefore, x equals ln of 6 divided by 0.6. And again, I would want you to leave your answer like this, but if you did put that into a calculator, it would approximately be equal to 2.99. In this one, we have, again, solving an exponential equation. I see two exponential functions. There's no way I can write them with the same base, which means I have to use natural logarithms to solve this problem. Now, first step is to isolate the exponential expression. Well, in both of these, they are both exponential expressions, and they just so happen to be isolated. So we've already finished that first step for us. Step 2 is to take the natural log of both sides. So I'm going to write the natural log of the left-hand side and the natural log of the right-hand side. Step 3 says figure out a way to isolate that variable. So I'm going to try and bring those exponents down front. So I'm going to bring x minus 2 over here and 2x plus 3 down in front here using the power property. So let me rewrite that. I have x minus 2 times ln of 5 equals 2x plus 3 times ln of 4. And then notice that I put them in parentheses. Make sure that you always write your binomials in parentheses. That way you don't accidentally think that it's only 2 times ln of 5. You know that it's the entire quantity of x minus 2 times ln of 5. All right, from there let's distribute the ln's to both of these. So we get ln of 5 times x minus 2 times ln of 5 equals 2 ln of 4 times x plus 3 ln of 4. Now, remember that the step that I'm on now, I already finished taking the natural log of both sides. I already simplified by bringing the exponents down front so that I have everything on the same level. And now my goal is solving for the variable. So notice that I have an x here and I have an x here. So in order to solve for that variable, I need to bring everything to one side of the equation. I should say everything that has a variable in it to one side of the equation and push everything else to the other side of the equation. So I'm going to move this to the left-hand side of the equation because I want that x on this side. And I'm going to move this term to this side of the equation because it does not have an x in it and I want all the constants on the right-hand side. So I have ln of 5 times x minus 2 ln of 4 times x equals 3 ln of 4 plus 2 ln of 5. So again, I just flip-flop these terms. I moved this term to the left and I moved this term to the right. And now I have an x in both of these terms. So the trick you can use in this case is that you can factor out an x. Because both of them have an x, we can factor out an x from both terms. So I'm left with x times ln of 5 minus 2 ln of 4 equals 3 ln of 4 plus 2 ln of 5. And again, I can factor out that x because it's a GCF from both of these terms here. After that, I want to get the x by itself. So I had it in two places, now I only have it in one place. And to finish us off, let's just divide by this constant here so that we have the x all by itself. So these equal 1, and I'm left with x equals 3 ln of 4. Move this down just a little bit so you guys can see it. 3 ln of 4 plus 2 ln of 5 divided by ln of 5 minus 2 ln of 4. And again, that is the closest you're going to get to a final answer. And if you put it into a calculator, you would get approximately negative 6.34. But again, for the purposes of what we're doing, I would like an exact answer. So I would rather have you leave your answer like this. All right, let's look at this example. So again, we have exponential functions in this, and you might think to yourself, hey, I need to isolate the exponential function, and you might see one here and one here, but then, there's a third function and it's not exponential. So, because we have multiple terms that are exponential, and not all of these terms we would be able to solve the normal way, we have to introduce a new strategy of solving these. So, instead of taking the natural log of both sides where we stand right now, we need to approach this from a different subject. So you might not be able to see this by looking at it readily or at the moment, but this next strategy that we're going to use is definitely going to help you guys in next semester, but also in future years of mathematics as well. So it's something called substitution. So I'm going to call it u substitution. So we're going to set u equal to some exponential function to kind of look at it in a different way. So I'm going to set u equal to e to the x. And we're going to look at how that alters this expression. So I have e to the power of 2x, or in other words, this is the same thing as e to the power of x squared, because the property of exponents says that you would multiply those. So 2x is the same thing as x, and then we'll have the 2 on the outside. Minus 4 times e to the power of x, and then plus 3 equals 0. So I can start making some substitutions for what u is equal to. So if I say u is equal to e to the power of x, I can replace each of those two terms with a u. So I'm going to rewrite this as u squared minus 4 times u plus 3 equals 0. And I hope now that it's a little bit more apparent to you that this is a quadratic equation. You might not have recognized it from up here, but now hopefully it makes sense to you that that's a quadratic equation. So this actually factors. It factors to u minus 3 times u minus 1. And if I use the zero product property, I can set each of these equal to 0. So I can say u minus 3 equals 0, and u minus 1 equals 0. And if I solve both of those equations, I get u equals 3, and u equals 1. And obviously, well, I hope it's obvious, we can't leave our answers like this because we know that u equals e to the power of x. So we have to go back and substitute e to the power of x back in everywhere I see a u. So I'm going to say e to the power of x equals 3, or e to the power of x equals 1. So one of those two things is true. So with that said, now that we have a simpler exponential equation, or in this case two simpler exponential equations, we can go back to our rules again. So step 1 was to isolate the exponential equation. Done. Step 2 was to take the natural log of both sides. So let's go ahead and do that. So ln of this equals ln of this, ln of this equals ln of this. Step 3 is to simplify somehow. So ln of e, remember log base e of e cancels. Again, not correct mathematically, but we can think about it like that. So this is just x equals ln of 3. Or log base e of e, which cancels to make x equals ln of 1. And I know that ln of 1 equals 0. So I have two solutions to this. And you can plug them back in to check to make sure they work in the original equation. But these are my two solutions to this exponential equation.